Great to have you back, and today we're going to nail down exactly how we calculate the speed of a traveling wave. So let us look at this wave at time t and then a small time interval delta t later. And what you see are two snapshots that show what the wave looks like at these two times. Now, this wave is traveling in the positive direction of x or to the right, and therefore we can see that the entire wave pattern has shifted a distance delta x in that interval delta t. So we can define the wave speed v as the ratio of distance delta x covered in time delta t. Or if you want to be more precise and look at the differential elements, we call it dx upon dt. However, the big question is, how can we actually find its value? So I want you to notice something interesting here. As the wave moves, each point of the moving waveform, let us take point A marked on a peak for example, actually retains its displacement y. Now be careful here because this quite often confuses students. Remember, the individual particles on the string are moving up and down. But here we are not tracking the particles. We are tracking the shape, the peak itself. And for that peak to keep its identity as it travels, the instruction to it is to maintain that height, that is, keep it constant. So getting back to point A, because point A keeps that same displacement as it travels, the phase in our equation that gives us the y position must remain a constant. That is, point A has to retain its y value, and for this to happen, kx minus omega t must remain a constant for A. Now you see, although this argument is constant, both x and t are changing simultaneously. So what is happening is, if you watch this expression closely, as time t is increasing, the position x is also increasing just to keep this argument constant. Well, this also mathematically confirms that the wave pattern is indeed moving in the positive direction of x. So to find the wave speed v, we simply take the derivative of this equation with respect to time. And when we do that, what we get is k dx upon dt minus omega equals 0. Or rearranging that, dx upon dt equals v equals omega upon k. Now, let's pull in what we know from our earlier work. We know that k is equal to 2 pi upon lambda and omega is equal to 2 pi upon t. Then we can rewrite the wave speed in a much more familiar way, that is, v is equal to omega upon k is equal to lambda upon t equals lambda f. And you see, this is a beautiful result. The equation v is equal to lambda upon t tells us quite clearly that the wave speed is exactly one wavelength per period. In other words, the wave moves a distance of one wavelength in one single period of oscillation. Now, I want to shift our focus for a second. We've been talking about an equation which describes a wave moving in the positive x direction. But what if the wave is going the other way? We can find the equation for a wave traveling in the opposite direction simply by replacing minus in this equation by a plus. And that leads us to a new condition. Kx plus omega t should equal a constant. And now for this argument to stay constant, x must decrease as time increases. That is, as t increases, x becomes more and more negative, offsetting the gain here. Thus, a wave traveling in the negative direction of x is described by the equation y of xt equals a sine kx plus omega t. Interestingly enough, if you analyze this wave the same way we did for the first one, you'll find its velocity to be dx upon dt equals minus omega upon k. And that minus sign is the key. It verifies that the wave is indeed moving in the negative direction of x and justifies why we switched the sign here in the first place. So as we wrap up, I want to leave you with a critical warning about this equation. This is a constraint equation, not a casual one. A lot of students look at this and think, oh, if I shake the rope twice as fast, doubling the frequency f, the wave will travel twice as fast. That is wrong. The speed of the wave v is determined strictly by the medium. In this case, the tension and the linear mass density of the string. The medium decides the speed limit, not your hand. So what happens if you double the frequency? The medium refuses to change the speed. Instead, the wavelength lambda is forced to cut in half to compensate. So lock this hierarchy in your mind. The source controls the frequency f, the medium controls the speed v. The wavelength lambda is just the result of the medium acting on the frequency. Understand this hierarchy and you won't just calculate wave motion, you will understand the physics behind it.